So my name is Ken Crozier. I'm from the School of Engineering and Applied Sciences, and the topic of my presentation is the optical antenna, a versatile tool for nanophotonics. It gives me great pleasure to acknowledge my research group, and today I'll be highlighting work done by Ethan Schönbrunn, Tian Yang and Charles Rinsler, and we have funding from DARPA, Schlumberger, NSF and Draper. So my group works on the development of photonics-based tools for nanotechnology. So currently in nanotechnology, what do we have to observe and manipulate structures? Well, using electron microscopes, we're able to see very small structures such as the different shells of this multi-walled carbon nanotube, and using scanning probe techniques such as a scanning tunneling microscope, we're able to image down to the level of the individual atom and even push around individual atoms, for example, to spell the letters IBM. At larger length scales, optics gives us a lot of functionality. With optical microscopy, we can fluorescently label different structures and get these beautiful images, for example, this one of a rat's retina. Using optical tweezers, we can apply optical forces and trap objects in a non-contact manner. And using spectroscopy, we can identify materials. And this sort of functionality with optics can be achieved at length scales greater than half a wavelength. What my group works on is translating this sort of functionality to the nanoscale. And this is a challenging thing to do. This is challenging because of the diffraction limit that tells us that if we have a lens, and even if it's a perfect lens free from aberrations, we can only focus the light to a spot of roughly half a wavelength. And that limits our ability to resolve very fine features with optical microscopes, the capacity of optical data storage, the minimum feature sizes in integrated circuits, and also our ability to manipulate objects with optical forces. So that's the challenge. So my group works on a structure that we call an optical antenna. And this is an antenna structure working at optical frequencies. And the idea is that we can use this structure to get a smaller spot. And the idea is illustrated in these diagrams here. So the top left is the case of focusing with the lens, where we can focus to a spot of roughly half a wavelength. And the bottom two diagrams illustrate the optical antenna concept, where we take that laser beam and direct it onto the antenna, excite oscillating surface currents leading to surface charges that generate fields that are confined to dimensions, as we'll see in today's presentation, of as small as tens of nanometers. And the idea is that we can then use those confined fields to make new types of microscopes, do ultra-sensitive spectroscopy, and potentially even manipulate very small particles. So today I'll be talking about this concept, and I'll be talking about a relatively recent device called a plasmonic laser antenna, consisting of a semiconductor laser with an optical antenna fabricated on the facet. And then I'll speak about applications of optical antennas, firstly as sensors, and I'll highlight a DNA sensor chip that's currently under development, and secondly as optical tweezers. And I'll talk about microfabricated structures for trapping nanoparticles with optical antennas and Fresnel zone plate optical tweezers that are useful for larger particles. So the idea of using an antenna structure to concentrate optical fields of very small dimensions was suggested by Grober and co-workers. And as a way of investigating this concept, they did some experiments at microwave frequencies at which the wavelength is considerably larger, and it's easier to prototype the structures as well as measure the field distributions. And so they worked at a free space wavelength of 14 centimeters, and they made this aluminum antenna, this aluminum bow tie antenna, consisting of these two triangular sections separated by a gap of 1 centimeter. And they put this in front of a waveguide, an open-ended waveguide. And then they measured the field distributions around that. Firstly, they measured that without the antenna, and they found that they could get a spot, which is shown here, of roughly a wavelength on either side. Then they placed the antenna in front of the waveguide, and they showed that they could concentrate the fields into the gap, and the size of the measured spot was lambda on 10 in one dimension by lambda on 6 in the other dimension, which is very exciting stuff because this is a spot with an area of roughly lambda squared on 60, far smaller than that what one can get with conventional means. And this was done with an efficiency of up to 30%. So that motivated us to see if we could translate this to the visible and near-infrared wavelength range. I should also mention in passing that there are a number of other structures in NSOM, or Near-Field Scanning Optical Microscopy, or SIRS, which is surface-enhanced Raman scattering, that could also be considered to be types of antennas. For example, in NSOM, one uses these sharp optical fibers that are coated up with metal, except at the very end where there's an aperture. One could consider that a type of antenna. And likewise, in apertureless or scattering, NSOM, one uses sharp tips to generate enhanced fields in small regions. One could consider that a type of antenna. As with the colloids that are used for field concentration in SIRS for ultrasensitive spectroscopy. So as I mentioned, that work by Grober and co-workers motivated us to move to the optical frequency range. And the first stop on that was the mid-infrared wavelength range. And so we started our investigations at wavelengths of about 10 microns. What I'm showing here are calculations, numerical electromagnetic calculations of the field distribution around an antenna structure that consists of a triangular section of gold that's on a silicon substrate. It's about 1.5 micron long. And it's illuminated through the substrate with a plane wave whose electric field is along this axis here. And what I'm plotting here is the intensity of the electric field, the square of the electric field, E squared, on the surface of the antenna. And it's normalized to the intensity of the incident wave. And what you see is that at the ends of the antenna, especially around this sharper end here, we have the field peaking up. And the peak value of the field is about 3,900 times that of the incident one. Well, that's the peak value of the square of the field. And if we zoom in at the end of the tip, then we see that these fields are confined to dimensions that are roughly 260 nanometers in this dimension, or lambda and 40 at the wavelength of operation, or 150 nanometers, or lambda and 70 in the other direction. And these dimensions correspond to roughly the radius of curvature at the end of the tip, which was chosen to be 120 nanometers, by about twice the radius of curvature. So this is telling us that this structure is really able to confine fields to dimensions that are given by how sharp a structure we can make, rather than any sort of wavelength limitation. So that motivated us to fabricate some of these devices. So we fabricated these antennas on silicon substrates. That scale bar there is 0.3 micron, and the total length of the antenna is about 1.5 micron. And to measure their wavelength response, we measured something called the extinction cross-section. Okay. So this is a cross-section, has units of area. When multiplied by the intensity of the input illumination, which is going to be in watts per meter squared, gives a power. And this represents the power that's removed or extinguished from the incident beam by the antenna through the process of scattering and absorption. It's equal to the sum of the scattering and absorption cross-sections. And what happens is that at a wavelength of this antenna, at a wavelength of approximately 10 micron, we hit a resonant condition for the antenna. So the fields, or the currents in the antenna, and also the near fields, that bright spot that I showed on the previous diagram, these are enhanced. And due to the enhanced currents, we also have an enhancement in the scattering because of the fact that the antenna radiates, and also in the absorption because of ohmic losses. So that leads to a peak in the extinction cross-section. So we were quite excited to see that the data, which is in the black, agreed very well with our modeling, which is in the green, the same modeling that was used to predict those enhanced fields around the antenna. And these two quantities are compared without any sort of fitting parameters. So it agreed quite well in terms of the position of the resonance as well as its peak. And that motivated us to see if we could make these antennas work at near-infrared and visible wavelengths, and also start to incorporate them in devices and use them in applications. So the first stop in that path was to work at the near-infrared wavelengths, and to do that we made the antennas much smaller. So now what I'm showing is a antenna, this bow tie that consists of these two gold triangles, and the triangles are approximately equilateral with an 88 nanometer side length. And the gap between the antenna is as small as 16 nanometers. And this antenna resonates, as shown here in the data in the calculation, in about 760 nanometers, so well into the near infrared, but with a much smaller structure. So I've shown single element antennas. I've also shown the two triangular sections, and I've shown some devices at mid-infrared and also at near-infrared. But in all of these cases, the basic operating principle is the same. We have a metallic section. We illuminate it with some sort of a wave, whose electric field is along this axis here. Electrons in the metal move under the influence of the electric field. So, for example, if the electric field is pointing this way, then we're going to have some net positive charge on one side, net negative charge on the other. Now let's consider this coupled antenna, these two gold rods or these two triangles. And let's think about this gap here. On one side of the gap, at some instant in time, we have positive charges. On the other side, we have negative charges. So in the vicinity of this structure, in the near field, we have electric fields that start on the positive charges, terminate on the negative charges, and they're confined to these small gaps or to the sharp ends of the structure. And so what that means is that if we can make a really small gap, then we can confine fields to a very small spot. Now, I'd like to tell you about some recent work that was done in a collaboration between my group and that of Professor Federico Capasso, and I'll talk about this collaboration in the next few slides. And it's on a device that we call the plasmonic laser antenna, and that consists of a semiconductor laser with an optical antenna fabricated on the facet, as shown here. Light comes from the laser, strikes the antenna, exciting those oscillating surface charges or surface plasmons, leading to an enhanced field inside the gap. This shows a simulation of the optical intensity, the square of electric field that's just calculated on the surface of the antenna, and it's normalized to the intensity, or the square of electric field, of the plane wave that would be transmitted in the absence of the antenna. What we see is that the fields are concentrated to the gap, and the gap in this case is 20 nanometers, and the peak value of that square of the field is 800 in that normalized to what would normally be transmitted. And I should mention that the antenna consists of two gold rods, each some 130 nanometers long. So we fabricated this device on the facet of a semiconductor laser. That was fairly challenging, but even more challenging is mapping out the fields. And to do this, we actually borrowed a technique that was originated here at CMU and published in this APL paper in 2003. And that's based on the principle that one can use a very sharp tip to scatter light. So clearly we can't just take this antenna device, switch it on, look at it under an optical microscope, because that's not going to be, we're not going to be able to image the near fields. That's just going to be looking at the far field of the antenna. So instead we use this technique, and it's called apertureless or scattering near field optical microscopy. And so what you do is you take a sharp silicon tip, and a commercial tip can easily have a radius of curvature of less than 10 nanometers. An oxidation sharpened tip can be as small as 2 nanometers, and you scan that across your structure. And the end of the tip is scattering light. And if you can pick up that scattered light as a function of your tip position, then you have a way of mapping out the field distributions. So we took our device, mounted it into an atomic force microscope, and we switched the device on. So this is it. This is the facet and the pair of rods at the end there. And we switch this laser on, and so there's a strong field generated inside that gap. And then we scan our atomic force microscope tip across this, and so the tip is scattering light. So when it's in the gap, it scatters a lot. When it's away from that, it doesn't scatter very much. We pick up the scattered light with a photodiode. We take that through a transimpedance amplifier, and then to a lock-in amplifier, and the reference signal to the lock-in amplifier is the signal from the position-sensitive photodetector that monitors that oscillation of the cantilever, because the cantilever is oscillating in tapping mode at about 300 kilohertz. And this allows us, using this lock-in amplifier, to pull from this photodiode signal the component that's due to scattering by the end of the tip. Because the tip is basically modulating that scattered light at 300 kilohertz. And that lock-in amplifier is somewhat similar to a bandpass filter operating at that 300 kilohertz, that oscillation frequency. And these are the results that we got. So the top left is the AFM image of the optical antenna. The top right is the SEM. There's two gold sections, each about 130 nanometers long, a gap of some 30 nanometers between them. And the bottom left is the near-field image of the optical antenna. And that's the output of that lock-in amplifier as a function of position of the tip. And I'm very excited when we got this result, because what we can see is that inside the gap of the antenna, we have a spot that's 40 nanometers across by 100 nanometers. And I should point out that this laser is operating at a free space wavelength of 830 nanometers. So with conventional optics, we'd only be able to focus down to approximately 415 nanometers, or roughly from about here to here. But with this optical antenna structure, we can concentrate the fields to a spot that has an area about a 50th of the diffraction limited spot. You also notice that there are fields at the ends of the antenna. One would expect some fields there. This is actually somewhat larger than we predicted theoretically, because there's also going to be charge at the ends of the antenna, leading to enhanced near fields. And so we're also interested in looking at, rather than a pair of rods, a bow tie structure, so two triangles, to try to spread out the charge at these opposite ends of the antenna to reduce those fields there. But we think there's a lot of possibilities. And one idea would be to use this in optical data storage. Now, certainly we're not there yet, but one idea would be to take one of these devices and position it above a disk. And currently we're at 40 by 100 nanometers. If we could get that down to a 20 nanometer spot size, and if we could write bits on a disk, then we would be able to store more than 3.6 terabytes in a disk the size of a CD. Actually, today I've been learning about another technique in magnetic recording, heat-assisted magnetic recording, or HAMR, that potentially this could also be useful for. Other applications include sensing and manipulation. I'll be talking about these in the remainder of my talk. So in the theme of sensing, my group is working under a center that we have at Harvard, funded by DARPA and industry, called the Harvard Center for Microfluidic and Plasmonic Systems. And we're working on an integrated DNA analysis chip that combines microfluidics with dielectric waveguides and with plasmon resonators, or optical antennas. And this chip is being designed and fabricated at Draper Lab, and my group is working on the design of the plasmon resonator structures, or optical antennas. So the idea is that we have some DNA, some double-stranded DNA. We attach some tags to it that attach to specific 7 or 8 base pair sequences. And we want to take this bit of DNA, run it through a chip that can tell us where along that strand of DNA those fluorescent tags are attached, as a way of doing sequencing of the DNA, but not trying to sequence every last little base, but doing a lower resolution DNA mapping that could allow us to work out from which organism this particular bit of DNA originates. Now, our collaborator US Genomics have developed a system for doing that, and they've shown that they can read these tags. However, their system is basically a conventional optical microscope that uses a microscope lens and is therefore diffraction limited, so can't really produce a spot of smaller than, say, quarter of a micron, or 250 nanometers. And that limits how closely we can put these tags along the DNA. So it'd be advantageous if we could put these much closer together. And that's where plasmons come in. So the idea is that we have this waveguide, we have the plasmon resonators, or optical antennas. The evanescent fields of the waveguide excite these plasmon resonances, leading to enhanced fields that are confined to very small dimensions. We've got down to 40 nanometers with that previous work. And if we could get down to similar dimensions with this work, then we'll be able to put the tags much closer together. And so we have the waveguide, we have the plasmon resonators, and we have DNA moving down this microfluidic channel, moving over the plasmon resonators, and the fluorescence from the tags is excited by the fields generated by these plasmon resonators. Now, in this illustration, I've shown several rows of these. I mean, that's what we're doing in our initial devices, but the final device will just be a single row of plasmon resonators. We're also looking at other designs here, but basically a single row of these that generates kind of a narrow stripe of illumination, much smaller than the wavelength, and it'll excite the fluorescence from the DNA. Now, as you can imagine, one can't just put a single antenna structure or plasmon resonator into that channel, because the DNA is not necessarily going to pass near it. So instead, we need to span the width of the microfluidic channel with enough of these plasmon resonators. But what happens when you do that is the plasmon resonances, the fields couple together. And that can lead to a significant modification in the plasmon resonant frequency, the frequency at which, if we illuminated that with light of that frequency, we can excite a very strongly enhanced fields around these particles. So we actually noticed some rather interesting behavior in this coupling behavior. And it's important for us to understand that so that we design these plasmon resonators appropriately to match to the fields in the waveguide. But it's also kind of more generally of interest to this field of plasmonics. So what do I mean by this coupling between plasmon resonators? So to understand that, let's consider if we have just a single metal nanoparticle or optical antenna. I've shown here a case of a gold nanosphere, and then we illuminate it with a wave. Okay? We illuminate it with a plane wave, for example, whose electric field is in this direction here. Well, the electrons in the sphere are going to move under the influence of the field. So at some instant in time, if the electric field is going in this direction, then electrons will move down, and we'll have some net negative charge at the bottom, net negative charge at the top. It's actually not necessarily going to be in phase like that, but that's the basic idea. So positive charge, negative charge, what would that remind you of? That would remind you of a dipole, and so it's actually like a little dipole. And it has a dipole moment that's equal to the free space permittivity multiplied by the polarizability of the particle multiplied by the incident electric field. But now we've displaced these charges. Okay? So there's a restoring force to re-establish charge neutrality, and so we can think about this as like a mass in a spring. We have a spring, has a certain spring constant, a mass in it, we displace it, and there's a restoring force. And just like a mass in a spring, there's a frequency associated with that, the plasmon frequency. And if we illuminate the structure with light of that frequency, then we'll excite this dipole very strongly, and it'll radiate. And this, for gold and silver, what's interesting is that these frequencies correspond to the visible part of the spectrum. So these particles scatter light very strongly in the visible wavelength range, and this has actually been used to produce some types of stained glass. Okay, so this is a single particle. Okay, so what happens if we have two particles close together? In that case, the fields couple together. So if these two particles close together, we illuminate them with a wave that has its electric field along this direction, and then we generate this dipole, and I've sketched out the fields from the dipole. But now let's consider this particle here. Now, it also has a dipole generated in it, and the dipole moment's also equal to this expression here, but now the field that drives it isn't just the field from the incident illumination. It's, in addition, the field from the neighboring nanoparticle. And so this couples the plasmon resonances together. And depending on whether the fields from the neighboring nanoparticle are in phase or out of phase with the fields that would be with the dipole that we generated just by the incident wave, that can either redshift or blue shift the plasmon frequency. And this has actually got quite a few applications in this field of plasmonics. One that's quite interesting is the so-called molecular ruler. And this comes from the group of Alivasatos at Berkeley. And what they did was they wanted to measure the distance, very small distances. Okay. So what they did was they put nanoparticles, attached nanoparticles to DNA. Attach these nanoparticles to DNA, and it turns out you can measure the distance between these nanoparticles by looking at the color of the scattered light. So they attached it to single-stranded DNA. Another strand comes in, hybridizes, forms double-stranded DNA. It's more rigid, pushes the nanoparticles apart by about a nanometer. But you can look at this in a dark field microscope, and you see, okay, now they're a bit further apart. They scatter light at a slightly different frequency. So the color of the scattered light's a little bit different, and they could resolve changes in distance of about a nanometer, hence molecular ruler. Okay? It's also important, this coupling process is also important in optical antennas, in the colloids used in surface-enhanced Raman scattering, and in some devices that were proposed by Quinton and co-workers that are basically waveguides based on chains of metal nanoparticles. So the idea is that you want to make a really small waveguide. Okay? You're not trying to make something that is going to compete with optical fibers, but rather you're going to make a waveguide that would be useful in situations where you really don't have a lot of room. And their idea is that we take a chain of these particles, we excite the plasmon resonance of one of them, this dipole excitation, first one. That couples to the next, and the next, and the next, and so forth. And in this way, you can transport electromagnetic energy down the chain of nanoparticles. And what's compelling is that these nanoparticles can have dimensions of just of tens of nanometers across. So they're not wavelength limited like conventional dielectric waveguides, where you'd have to have a mode size of about lambda, the wavelength, divided by the refractive index. So in these structures, as far as we know it, prior to this work, no prior experimental work had been done on how the plasmon resonance frequencies of metal nanoparticle chains varied as a function of K vector. What people had looked at is how these vary as a function of separation, for example, in the molecular order, or refractive index, for refractive index sensing, but no one's actually looked at how they vary with K vector. Now, this is a very important problem to us because in our design of this chip, we have a K vector inside the waveguide. We've got to match it to the K vector along the plasmon resonance structure. Otherwise, we're not going to couple to that resonance where we get these greatly enhanced fields that we're going to be using for fluorescence excitation. And it's also important in metal nanoparticle chain waveguides to look at the matching and group velocity and so forth. So the variation of the plasmon frequency with K vector, by that I mean the K vector along the chain, the component that's along the chain of nanoparticles, is represented by something called the dispersion relation that maps out the plasmon frequency as a function of K vector. And this is the same dispersion relation that you have for waveguides. And there's actually, it turns out that when we started to look at this problem, we realized that there's a number of models in the literature. And there's actually not good agreement in terms of what is that dispersion relation. How does that plasmon frequency vary as a function of K vector? And so what I'm showing here is from the paper of Kunderink and Polman, who looked at the different models that are in the literature. And each of these different curves or different symbols is basically a different theory about what is that dispersion relation. But we really need to know this because we need to know this for our chip. So our response was we really got to look at this experimentally to work out what is that dispersion relation. So we fabricated gold nanoparticle chains on glass slides by electron beam lithography. The nanoparticles are cylinders with diameters of 92 nanometers, and the spacing along the chain is 140 nanometers. For experimental convenience, we make arrays of these chains rather than just single chains, and adjacent chains are spaced by 300 nanometers. And these are zoom-ins of the structures. The entire structure occupies a region of 100 by 100 micron. And then we take light from a xenon lamp, we take it through an optical fiber, take the output from the fiber, collimate it, and transmit it through our sample. So we have our nanoparticle chain array sitting here. And this is a color photograph of that sample, 100 by 100 micron. And we collect the transmitted light into an optical spectrum analyzer, and we measure the transmission, and this is the results that we get. So this is transmission as a function of wavelength measured for these nanoparticle chains. The blue curve is when we have the polarization perpendicular to the chain. The red curve is when it's along the direction of the chain. And you notice there's a dip in transmission. So what's happening there? What's happening is that at this wavelength or frequency, we're coupling to the plasmon resonance. Okay, so we couple to the plasmon resonance at that frequency to get those electrons oscillating in those enhanced fields, and that leads to a drop in the transmission. But what's interesting is that depending on whether we're polarized perpendicular to the chain, this blue curve, or parallel to the chain, we have different plasmon frequencies that are either at 589 nanometers for the transverse mode or 625 nanometers for the longitudinal mode. And this isn't due to the particles being asymmetric or anything like that. To understand this, let's think about some particles in a chain and think about the dipoles, that are excited. Let's firstly think about that transverse mode where we're polarized perpendicular to the chain. Let's think what happens at normal incidence. And let's consider a dipole and its neighbors. So let's consider this dipole here. The arrows represent the direction of the dipole moment. And these, I've sketched here the fields from the neighboring dipoles. So we can see that for this transverse mode, the fields from the neighboring nanoparticles are in a direction that's opposite to the dipole moment. That blue shifts the plasmon frequency. For the case of the longitudinal mode, the fields at the dipole are in the same direction as the dipole moment. That redshifts the plasmon frequency. So that's why this mode is at the 625 and the other mode was at the 589 nanometers. So how about measuring this dispersion? Well, to do that, we take our sample and we make transmission measurements through the sample, but we vary the angle of incidence. So we start at normal incidence. Theta is equal to 0, that's this curve here. And in that case, k along the chain is equal to 0. They're all excited interface. And then we vary this angle from 0 to 75 degrees in steps of 5 degrees. And we make these measurements. And we do this for S polarization. We do this for P polarization. The S polarization picks up the one transverse mode. The P polarization at normal incidence picks up the longitudinal mode. All these dipoles are all aligned along the chain of the nanoparticles. And at larger angles, it picks up the second transverse mode. And we look at the position of the plasmon resonance in terms of wavelength. We can convert that to plasmon frequency. And by knowing the angle of incidence, we can also find the in-plane k vector, or 2 pi divided by lambda multiplied by sine of that angle. And this is what we got. So we got this for the transverse mode in the blue, for the longitudinal mode in the red. And so this is frequency, this is normalized in-plane wave vector, this is going from normal incidence at 0 degrees up to 75 degrees. This dotted line is called the light line of air, and it corresponds to the condition of k is equal to 2 pi on lambda, and this would correspond to if we came in at 90 degrees. Okay. So we thought, okay, how do these models compare to those theoretical models in the literature? So we compared it with the best available model that we had, made the fewest assumptions. But those models are all developed for the case of nanoparticles in a homogeneous medium. Whereas in our case, we have the nanoparticles fabricated on a glass substrate. So if we look at the cross-section, we notice that there's glass on one side, nanoparticles, air on the other side. So what do we compare it to? Because the models are for a homogeneous medium. So what we do is we compare it to, firstly, we do the calculations for nanoparticles just in air. And this gives us this, the black and the green curves. And then we compare it to the case for nanoparticles in a homogeneous medium. And so we get this, these characteristic curves, this cyan and the magenta curves. And so initially we thought, okay, this seems consistent. So in our case, we have nanoparticles at the interface between two media. So okay, our curves are in between these two cases. It seems consistent. But what we're interested in doing there is measuring beyond this light line of air that we get through transmission measurements to get the larger k vectors. Because in transmission, all we can get to is maximum k vector along the chain of 2 pi on lambda. If we come in through the sample with total internal reflection, then we can get up to the light line of glass, 2 pi n on lambda. And this region corresponds to the total internal reflection region that's appropriate for our waveguide application. Right? Because we're going to have larger k vectors than the k vectors in air. So we put a prism into the setup. And we made our reflection measurements. And then we kept on measuring in this region here, this total internal reflection regime, and we noticed something that was very striking. And this is for the transverse mode. We noticed that as we cross into this total internal reflection regime, we get quite an abrupt change in the plasmon frequency as a function of k vector. That's not predicted by the models that that simply do not predict that. So we initially thought, okay, maybe there's something wrong with our experiments. So we did a lot of numerical modeling using the finite difference time domain method to model this, and the results are shown in the orange symbols here. We found, sure enough, it agrees very well with our experiments, so it's not a problem with our experiments. But then we thought about it a bit more, and we thought, okay, these things really are like little dipole antennas. But what's not captured in those other models is the other models are looking for a dipole in a homogeneous medium. But the dipoles are, in fact, at the interface between two media. And the problem of a dipole at a half space at the interface between two media it's a real classic problem in antenna engineering that's been thought about since 1909. Of course, in 1909, Sommerfeld was thinking about radio wave antennas at the surface of the Earth, so at the interface between Earth and the air, rather than metal nanoparticles at glass air interface. but it's a problem, it's a real classic problem in antenna engineering, and it turns out that the fields around these dipoles are considerably modified by the presence of that interface. And despite the almost 100-year history of the problem, there's actually no closed-form analytical, no compact analytical solution. In the far field, far away from the dipole, one can approximate this very nicely. And it turns out that if we, for example, we're looking at the fields in this upper half space, then we see that they can be decomposed into a superposition of a direct field from this dipole, this P, this red arrow here, and an indirect pathway where the fields are radiated and they're reflected by this glass air interface, and the total field is the superposition of these. In the near field, one does similar sort of thing, but one also includes the evanescent waves. But in both of those cases, we weight those fields by the Fresnel reflection coefficients. And that's the clue to understanding what's going on with that very abrupt change in the dispersion. So if we look at the Fresnel reflection coefficients for a plane wave, S-polarized plane wave, at the interface between glass and the air, we can look at the amplitude and look at the phase. And we can look at this as a function of k vector, where we go from 0 to k vector corresponding to angle of incidence of 90 degrees. We can go to beyond that corresponds to the case of evanescent waves. And if we look at the phase, and we see that the phase of a reflected wave varies quite markedly in this larger k vector region, that region that corresponds to the region between those two light lines. So that's a clue to what's going on. So this is a zoom in of the, well, it's an expanded scale, I should say, of the calculations in the green and the experiments in the orange of these nanoparticles, the transverse mode, the dispersion relation of the transverse mode. And so you can see even more clearly on the scale that we have this abrupt change in the dispersion. So what's happening there is that the nanoparticles are creating, they're radiating plane waves, they're creating evanescent waves. These waves are reflected by that interface and they pick up a phase change. And so if we return back to our model of the plasmon resonance frequency by considering the fields from the neighboring nanoparticles at the position of the dipole, the fact that these phases are changing so rapidly as a function of k vector means that we have a rapid change in the plasmon frequency. Because remember, phase is very important. Depending on whether the fields from the neighboring nanoparticles are in the same direction as the dipole or opposite to it, that changes whether or not the plasmon frequency is redshifted or blue shifted. So it's quite interesting for us that we could get a lot of insight by thinking about antenna engineering there. So in the last section of my talk, I'd like to talk about optical manipulation at the nanoscale. So by that, we're interested in developing new types of microfabricated structures useful for trapping and manipulating nanoparticles and microparticles, like optical tweezer. So with conventional optical tweezers, one takes a high numerical aperture microscope lens and focuses a laser down to a small spot. And a particle in the vicinity of the focused spot will experience a gradient force, and the force is proportional to the polarizability of the particle multiplied by the gradient of the intensity. Associated with that gradient force is a potential energy, which is just equal to that polarizability divided by 2 multiplied by the intensity. And so this is what draws the particle into the focus and traps it there. But to trap a particle in the presence of Brownian motion, one needs this potential energy greater than some value of kT, greater than a few kT, or perhaps 10 kT. So the polarizability of the particle is proportional to its volume. So for a small particle, one needs a high laser power. So for example, ash can trap 26 nanometer nanoparticles with a laser power of more than a watt. So we'd like to reduce that power. And what we're interested in doing is using this optical nano antenna to generate an intense field by laser illumination that could be used to trap particles in the focus there. So I'm interested in trapping particles with sizes of 100 nanometers or less, perhaps even single virus particles with diameters of 20 nanometers. And so how would this work? Well, what I've shown here are calculations of the trapping force on a dipole that represents a bead of 10 nanometer radius by an antenna consisting of these two gold rods, each about 130 nanometers long, separated by a gap of 20 nanometers. The green arrows represent the directions of the force. The color coding represents the magnitude of the force. What you see is that the particle will be drawn either into the gap or into the ends of the antenna structure, and it'll be trapped there. And this is for an input illumination of 10 milliwatts per micron squared at a free space wavelength of 830 nanometers. So how might we want to use this? Well, our idea is that we could put these antenna structures at the bottom of a microfluidic channel and use the channel to flow particles across this array of antennas. A mixture of particles of various sizes. The particles that are small enough to fit inside the gap will be drawn by those optical forces into the gap and trapped there. Particles that are too large will only experience these enhanced fields over the very extremities of their volume, so there wouldn't be sufficient force to trap those, and particles that are too small, there wouldn't be enough polarizability to trap them. So we'd flow these particles of various sizes across this array of traps, draw down the small particles, trap them in there, and then once all these antennas are full, well, they're all populated with the particles, then we'd turn off the laser, release them, and collect these nanoparticles. We're also interested in trapping larger structures, and for that we don't necessarily need optical antennas. So to do that, we're investigating zone plates, Fresnel zone plates. And I've shown some fabricated devices here. So we have a device that consists of alternating, rings, gold rings basically, gold rings that block the light, and in between the gold rings we just have glass that shows in this optical photograph or as being black, but it's just a glass region that transmits light. And this shows the concept. So it would come in with a laser beam which would strike this Fresnel zone plate, and then there's diffraction from the openings, and the radii of these rings are chosen such that these diffracted waves interfere constructively at the focal point to form a spot of about 300 nanometers or so, which we would use to trap a bead. Okay. Now this device is 100 microns wide. The focal length is designed to be 8 microns, so it actually has a very high numerical aperture. The numerical aperture, calculated numerical aperture, is about 1.31, so actually very close to the refractive index of the water itself. And these are designed for a free space wavelength of 976 nanometers, but they're designed to be operating in a water environment. And so we set up a system to demonstrate trapping with these Fresnel zone plates. We take light from a fiber-coupled diode laser, expand it up, and then, so it's expanded and collimated. It then illuminates the Fresnel zone plate, and then that Fresnel zone plate focuses the beam down to a small spot, which traps a bead. And then from the other side, we have two lasers. The green laser excites fluorescence from the bead. That's then imaged by a microscope objective onto a CCD camera, and that allows us to track the bead position as a function of time. We also use another laser to push the bead onto the glass surface. At that point, we turn it off, the bead floats up, and then it's trapped by the Fresnel zone plate, and then we make our observations of the trapping as a function of time. And so here are some photographs. It's a little bit hard to see, but you can see a bright spot here. That's a trapped bead. You're not going to be able to see that there, but they have the outline of the Fresnel zone plate. And well, let's just see if this... well, maybe you can see the bead moving around there. That's a trapped bead. There's also some other beads that are not trapped, and they just float through the field of view. So how well does this work? To work out how well... Oh, okay. Thanks very much. So you can see a trapped bead there. So this is moving around due to Brownian motion. And there's another bead that is just moving around here. It's moving out of the field of view because it's not trapped. And yeah, so that's that image. And perhaps you can see a bit better now the outline of the Fresnel zone plate. So how well do these work? To look at that, we look at the position as a function of time. And we get this by analyzing those fluorescent images. And so this shows the position as a function of time. The scale that there is in nanometers. And we have 3 traces measured for laser powers in the blue of 20 milliwatts, in the green 60 milliwatts, in the red 180 milliwatts. This is the power from the laser. And we can see that at the higher laser powers, you can trap to less than 50 nanometers or so. This work is going to appear in APL later this month. And the performance of the trap, the stiffness of the trap, is about 10% that of a very high a numerical aperture microscope lens, and that factor of 10 is due to the diffraction efficiency of the Fresnel zone plate being about 1 on pi squared. If we use a phase zone plate, then we could get that up to 4 on pi squared, or about 40%, and that's actually as good as the transmission of a lot of microscope lenses. So we have comparable performance, though we take a bit of a hit with the diffraction efficiency. So to summarize, we've seen that optical antennas in nanophotonics allow us to confine to fields of tens of nanometers. 40 by 100 nanometers has been demonstrated. We've seen that these, the surface plasmon excitations of these nanoparticles, one needs to carefully consider the neighboring nanoparticles as well as the environment, both the substrate and the medium above the substrate, to understand how the plasmon resonance frequencies, what the plasmon resonance frequencies are. And we've seen that they're highly k-vector dependent. And that's important in applications where you're coupling from a waveguide. And lastly, I think there's a lot of possibilities in microfluidic optical tweezers based on antenna structures for nanoparticles and Fresnel zone plates for microparticles. So to conclude, I really think that the optical antenna should allow us to develop new types of sensing tools, manipulation and imaging tools. But in all of these, it's quite encouraging to double E people at least, that in a field that's kind of dominated, the field of plasmonics kind of dominated by the chemists, and it's kind of nice to know that antenna engineering can really help us in designing devices and interpreting behavior. So thanks very much. That concludes my presentation.
For that little antenna on the laser facet, what's the angular spread of the light coming out from the gap?
We've never measured that, but it would be pretty wide. I mean, it'd be like that of half-wave dipole type of dipole antenna, so it'd be pretty wide.
That will impact your applications, because let's say for the DNA thing, DNA has to...
No, in that application, what we're really trying to do there is have the DNA flow over that structure, really in the near field. So we're also looking at structures, rather than these arrays of dots, a single stripe of metal, and exciting the plasmon resonance of that. So the field really is on the surface, and really interested in getting that DNA right onto the, right just above that surface. For the other applications, such as the data storage one would really need the data storage medium to be in the near field, so roughly within the size of the spot. But for magnetic recording, I mean, that's the air-bearing type of approaches, that would work very well for that.
I'm curious of some of your earlier bow tie antennas. Why you selected to just look at half the bow tie instead of both sides?
Right.
Single triangular elements to make it belong to this pure image.
Well, I mean, we're interested in various applications there. Another project that I have is on putting antennas onto AFM tips. In that case, it's just a single kind of cone-type structure. And the idea is that one could make a much sharper tip than one could make if one tried to have the antenna kind of flat on the surface there. So, the dipole antenna structure gives a very large enhancement, but you also can get a large enhancement just with a sharp single element structure, where you have this fields. We have the end of the structure coming to a very sharp tip, meaning that the charges are only spread out over a very small surface area, leading to a high surface charge density and hence a large near field.
Is there a significant difference in the bandwidth of the enhancement? One of the advantages of a bow tie antenna is it doesn't have a narrow resonance. It works over a wide range
Both the single element structures also actually have a very wide bandwidth, and we've seen that by looking at that extinction cross section, as well as calculations for the near field as a function of wavelength or frequency.
So I forgot that when you have this 40 nanometer size, what is the gap between two electrodes?
It's about 30 nanometers or so. So some of that could be the finite size at the end of the tip that's used to probe this. We use a sharp silicon tip, but then we metallize it so it scatters more. So
my question is, if you make this gap smaller,
right.
you predict the size is going to be smaller.
Right. And the fields can get extremely large. I mean, there's quite a bit of work that's been done in the context of surface-enhanced Raman scattering, where people have looked at gaps of 2 nanometers or so that could actually occur in colloidal particles. It's a bit harder to fabricate. Well, I mean, there are ways one could fabricate that, but.
This is my next question. Imagine the field is very strong.
Right.
Actually, we now can make gaps down to like 2-3 nanometers between a pair of electrodes.
Right.
So just from her perspective, like, I'm just curious, how strong a field that can be, or
well, I mean, I guess in the field of surface-enhanced Raman scattering, people have done those sort of calculations and predicted with gaps of 2 nanometers or so, they can, maybe the largest field that I've seen calculated is for the square of the field being about 10 to the 6 times that of the incident field. So in our calculations for the 20 nanometer gap size, we calculated about 10 to the 3. But if we get even smaller, then we can potentially could get even larger than that. And there's been a little bit of work done where they've used electromigration to make small gaps, but the structures weren't so nice. But there's been some work done at spectroscopy of molecules in those gaps.
So, as we were talking about earlier today, one of the things which in the hammer application, in the recording application, is that the media comes along and sort of loads the antenna very substantially, completely changing the resonance and the conditions under which it can operate. Do you, in some of these biological applications, is there an anticipation that as the DNA molecule or the virus or something comes in, that it's going to sort of load the antenna to the extent that you have to redesign it to give the right impedance after it's loaded?
Sure. So in our case, for the DNA microfluidic chip, we include the water in our calculations, and that shifts the plasmon resonances. We don't include the DNA. I mean, the DNA is pretty small compared to the antenna. There's another project that's actually not in my group. It's part of this DARPA center that we have, but it kind of illustrates your point. And what this is a group in Harvard Medical School, Dale Larson. What he's doing there is he's making plasmon structures consisting of nanohole arrays in a gold film. He puts a lipid bilayer onto the surface, and what he wants to do is look at interactions between single virus particles attaching to that lipid bilayer, changing their conformation, trying to inject their material into the lipid bilayer. And the idea there is that we can observe this process by measuring the transmission through these holes. Because the idea is as this virus comes in, changes the local refractive index, that shifts the plasmon frequency a bit, and so that means that changes the transmission through this array of holes. So potentially, the people have used this for refractive index sensing before, mainly for bulk liquids, but applications where you functionalize the surface and then look at interactions, I think it could be quite interesting. And one can think about that as being impedance loading type of behavior.
In typical semiconductor lasers, the field strengths can get up to about 10 to the 7 on the fastest. If you concentrate, then you run the risk of getting to the passive structure optical damage range. Have you reached that yet?
Well, we've in our initial measurements with the antenna on the laser, what we found is we melted a lot of the antennas, as you might expect, because the fields are so large, right? So, and that's a fairly extreme case of damage. So the results that I've shown were obtained with average power from the laser of 0.3 milliwatts. Okay, so even at that level, one can get very strong, well calculated, very strong fields inside the gap, a very bright spot, and we've calculated that it should be enough for optical data storage. I would have to look at heat-assisted magnetic recording, but yeah. So there's and so other things that could be done is looking at other designs where one has a lot of metal, and then maybe one of these antenna structures inside another aperture for more dissipation there. And we were talking about that this morning with Jim and I were talking about that.
If there aren't any questions, let's thank our speaker again.
Great, thanks very much.